Hello again. We are now going to take what we learned about differentials and we're going to apply it to what we call linearization. When we did differentials, the differentials told us how much y changed by if we changed x by a little bit. Well, with linearization now, what we're going to do is we're going to find not how much the y changes, but the actual y value if the x changes. So I have a problem posted here, and we are going to use linearization to approximate the cube root of 8.1. So if you look at the picture I have posted over here, you'll see that the red is the cube root of x, and the green line is the tangent line to this cube root function at the point 8. And if you look at that tangent line and that cube third root function, they look to be almost identical, right around the point where they are tangent. So that's the theory behind all of this. We're going to use the tangent line to approximate the value of the cubed root function for values close to 8. Alright, so we're going to come back here and we're going to find that equation for the tangent line, or the green function. Well, we are working with the cube root function. We know if we have an x value, or a special x value of a equaling 8, we know the answer is 2. But what if we change the 8? What if we change our x value by 0.1? What happens? Now, in the last video, we found dy. In this video, we want to actually find the new value of y, not just how much it changes by. So we're going to do that by using the tangent line, which is given by y minus y1 equals m times x minus x1. All right, now here is my point of tangency. So that's what's going to go in for x1 and y1. So we'll get y minus 2 equals m times x minus 8. Our slope is just found by taking our derivative. So the derivative of our function is 1 over 3x to the 2/3. Now you can stop the video real quick and double check, make sure you understand where that came from. And now we're going to actually plug in our x value, which was 8. And that value is going to be 1/12. So we can plug that in and get the equation of our tangent line. So it's going to look like, oops, hang on one sec. It's going to look like y minus 2 equals 1/12 times x minus 8. Now remember, we're using this tangent line to figure out what our new y value is going to be if we change x by 0.1. So I'm going to go ahead and get y alone here by adding 2 to both sides. And that is the equation of that green line up there. What we want to know now is what happens if I plug in 8.1 into that equation. We will get the value of the green line when x is 8.1, which is so incredibly close to the red line that that's where our good approximation is going to come from. So if I plug that in right now, I'm going to get y equals, our new value will be 1/12. Now if I put 8.1 in there, I'll get 8.1 minus 8, which is 0.1, plus 2. So this is where the differentials is going to come in. If you remember from the last video, this part right there is basically, if you look at it and think about it, that 1/12 is my f prime at my x value, 8. My 0.1 is just the change in x. We got 0.1 from going from 8 to 8.1, which is 0.1 units. So really, if I want to know just how much y is going to change by, it would be that highlighted yellow bit, which would be, what would that be? 1 over 120. But the new y value comes when we add in the original height, or the original amount the y was before we changed. So we're going to get our new y value is how much the y changed by plus what the y value was before we started, which was not 8. Don't know why I put that. It was 2. So our new y value will be 2 and 1 over 1/20. Okay, so here is another example. We want to use linearization to approximate 2.99 cubed. So the function that, the function that we're looking at on this one is f of x equals something cubed. And we know that if we cubed 3, which is close to 2.99, so we're going to let a be 3, then that would be pretty easy. Y would be 27. But we really don't want to know when x is 3. We want to know when x is 2.99. So that's going to be a difference of negative 0.01. So we're going to find our equation of our tangent line at this point of tangency, and then we're going to plug in 2.99 into the tangent line equation to get the value of the tangent line there, which will be close enough to the cubed function, x to the third. So let's do that. We have y minus y1 equals m times x minus x1. We know y1 is 27. Sorry. Y minus 27, x minus 3. And we have a derivative that we need, which is a pretty simple one. It's just 3x squared. Our derivative at our point of tangency is going to be 27. So when we put that all together, we get our equation of our tangent line. X minus 3. And then to get y alone, so that we can figure out what our new y value will be, it's going to be this plus 27. And again, I just want to re-emphasize that this bit right here is just how much y will change by. That is just our f prime at a, and this is going to be our dx when we stick in 2.99. That's going to turn out to be our negative 0.01. So I'm going to go up here to finish this off. Our new y value will be 27. And again, I'm going to put 2.99 in there. So that's going to be negative 0.01. So our change, that's how much y will change by. And then we'll add the 27 to get our new y. And I don't know what this is going to be. Let's see, 27 times negative 1 over 100 plus 27. And you can figure it out from there, but negative 0.27 plus 27. So it's a little under 27, which is what we would expect. I hope that makes linearization crystal clear.